In the last video, we figured out how to write Taylor polynomials in general terms in a Taylor series for functions that came from various forms of 1 over 1 minus x. And that was great as long as it fit that format of being 1 over 1 minus x, 1 over 1 plus x, 1 over 1 minus 2x, things like that. Oddly enough, there's other functions in the world besides 1 over 1 minus x. If we want to write a Taylor polynomial for them, how do we do that? So I'm going to try this on this whiteboard and this little marker device here. And if this works out well, you're seeing it now. And if it was a complete disaster, then you're not seeing this because I've deleted it and started again. So let's start with what we know in terms of a definition of a series. We're going to look at the series from n equals 0 to infinity of c sub n x minus a to the n. And I'm going to call that function f of x, and I'm going to write it out as a function. I'm going to write out a bunch of terms, and I'm doing it for a reason. So f of x is going to be c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared. And I'm doing this whole thing written out because when I get to the formula at the very end, it's going to take me a few minutes to get there. When I get to the formula at the very end, if I had just given you that formula, I don't think you would believe me. So I better explain it. All right, the first thing I'm going to do is I'm going to take the first derivative. So the first derivative, well, that constant's going to go away, right? Over here, c sub 1 times x minus a, when I derive the c sub 1 times a, that's just a constant. So really what I end up with for the first term is just a c sub 1, right? The derivative of c sub 1 times x is c sub 1. The second one then, I'll use the power rule, right? 2 times c sub 2 x minus a to the first. The next one will give me a 3 c sub 3 x minus a to the second. I'll get a 4 c sub 4 x minus a to the third, and so forth. All right, let's derive it again. I'm going to probably take 3 or 4 derivatives, so we may have to get creative because we're going to run out of terms after a while. The 2c sub 2 stays, right? 2c sub 2. Then the next term becomes 3 times 2 c sub 3 x minus a to the first. The next one becomes 4 times 3 c sub 4 x minus a to the second. And if you now took another derivative, right, took the third derivative with respect to x, the 2c sub 2 goes away. Our first term now is 3 times 2 times c sub 3, right? That's coming from this term over here, right? When I derive that, that's what I get. Then the next one will end up being 4 times 3 times 2 c sub 4 x minus a, and it continues from there, right? These are all going on and on and on. All right, should we do one more? Suppose I took the fourth derivative with respect to x. I would end up with 4 times 3 times 2 c sub 4, and then it would continue on from there. All right, so why in the world am I doing this? Suppose I took this whole thing and I said, great, I want to write a function centered at a. So for each of these guys over here, I would now like to find me f of a. When I do that, do you realize that everything goes away except for these pieces over here? Right? Because if I evaluate this thing at x equals a, then I end up with a minus a, which is 0, a minus a, which is 0. All these x minus a's go away when I evaluate it at f of a. So here, let's move this up and rewrite everything in terms of a. So if I go back to where I started, f of a is going to be c sub 0, and f prime of a is going to be c sub 1. So f of a is c sub 0. F prime of a is going to be c sub 1. F double prime of a then will be 2 times c sub 2. F triple prime of a will be, well, notice we got 3 times 2 times c sub 3, so let's call it 3 factorial times c sub 3. Would it be any harm if I called this 2 factorial times c sub 2? And then the fourth derivative centered at a is going to be 4 factorial, right? Because that 4 times 3 times 2, that's 4 factorial c sub 4. Beautiful. Now, let's move this over to the next column. This time, instead of solving for the f of a's and the f prime of a's, I want to solve for the constants. Okay, so I'm going to write, instead of f of a equals c sub 0, the first couple look a little silly because you're like, where is this going? So c sub 0 is f of a. C sub 1 is f prime of a. All right, now, c sub 2, in order to get that, we're going to have to come here and divide both sides by 2 factorial. So I'll get f double prime of a over 2 factorial. C sub 3, then, will be f triple prime of a over 3 factorial. And if I can fit it, c sub 4 will be the fourth derivative evaluated at a over 4 factorial. Okay, good. We're almost there. Go back to the original expression that I had up at the top, right? The f of x equals c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared. We're going to come back to that very expression up there, except this time, every time we have a c sub 1 and a c sub 0 and a c sub 2, we're going to replace it with those terms that we had down the bottom. All right, so these guys in blue over here, f of a, f prime of a, f double prime of a, that's what we're going to replace. So let's try it. We said that f of x was c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared plus c sub 3 times x minus a to the third plus c sub 4 x minus a to the fourth, and so forth. All right, replace those coefficients, and I get f of x equals that c sub 0 is f of a, right? Go back to my first blue guy up here. C sub 0 is f of a, and the c sub 1 is f prime of a. So I end up with f of a plus f prime of a x minus a plus f double prime of a x minus a squared, except realize that that f double prime is over 2 factorial. And the f triple prime is over 3 factorial. And you can see that if I did the quadruple prime, that would be divided by 4 factorial. So what have I created? I've created this formula that must be forever in your memories. And if you keep going, by the way, there's an nth term at the end of all this too, which clearly I've run out of space for. So the nth term would be the nth derivative evaluated at a, x minus a to the n over n factorial, right? So this thing here is the Taylor series for the function centered at x minus a. So when you're asked to create a Taylor series, right, the Taylor series, or if you want just part of it, you're looking for the Taylor polynomial, centered at x equals a. And that is the formula that you're going to need to commit to memory. And that is the f of a, f prime of a, x minus a, f double prime of a, x minus a squared over 2 factorial, f triple prime, and so forth and so on. Interesting thing comes out of this, right? Look at the first couple of terms. I want to do that. Look at the first couple of terms of this series, right? F of x equals f of a plus f prime of a x minus a. Doesn't that look like point slope form for a line? That f prime of a is the slope, isn't it? And from there you can distribute and get a y-intercept and so forth. The other thing is, remember back in Calc 1 you did linearization and you created a line that was a tangent line to a graph that was centered at a certain point? Wasn't this the formula that you used for linearization? Linearization is essentially a first-degree Taylor polynomial. And we label these, by the way, as degrees. So you can, or orders, to do that too. So this is a first order or a first degree Taylor polynomial. It is also the formula that's used in Calc 1 for linearization, which is kind of a neat connection. Then you realize the second one then will be a quadratic approximation. So you'll have your f prime of ax minus a, the f double prime x minus a squared, so that'll be a second degree and so forth. So there is a connection, a nice connection between this and the material that you did in Calc 1. All right, I'm going to move on to the third part of this, which is, hang on to your hats, we're actually going to create Taylor polynomials for various functions besides 1 over 1 minus x.